more detail about some of these systems that I've mentioned. First is bone. It's probably something you've all heard about that changes with microgravity or unloading. When you take normal loading away from bone, it starts to change. There's a phrase that you may have heard, you don't use it, you lose it. That's kind of similar to calculus for me. If I don't use calculus, I start to lose it. And the same is true for bone strength. If you're not using your bones and challenging them and loading them through weightlifting or just gravity loading, they start to get weak. Now, this is a process that happens in a lot of people here on Earth. The disease called osteoporosis. It affects a lot of Americans, and mostly women. What does that mean? What? Well, it means if you have to get all, break them.
Hang on. We're having massive technical difficulty. Hold on.
Okay. Yeah, sorry about the comm delay. It's that's something we have to deal with in space too. So, when you start to lose bone, there's a couple of things that happen. Your bones get a little, the spaces between the small bone fibers get larger. The bone fibers themselves get smaller. And the other thing that happens is all that bone, what's happening exactly? Well, calcium is starting to leave your bones and go into your bloodstream. That's not too much of a bad thing, except that calcium can become solidified elsewhere, and it may become solidified in your kidneys. And if you've ever heard of someone having a kidney stone, or if you've ever experienced one, when they pass, it is one of the most excruciating pains you can imagine. And that, if it happens in space, it could be a real showstopper to have someone in real pain and basically out of commission for a while. It's fortunately not life-threatening per se, but it could certainly impact the way someone can do their job in space. So how much bone do astronauts lose in space? Let's check the next slide. Okay, well, you can see that it depends on what kind of bone we're talking about. In other words, it's region and function dependent. The bone, let's see, the green line that extends furthest from the right to the left represents the most change in bone mineral density. That's the Bravo, the change in bone, BMD, that's the bone mineral density. That's femoral trochanter is what that green bar is. That's the upper part of your femur, the long leg bone that goes into your pelvis. The next largest change is the pelvis, and then spine and femoral neck. So those are long bones in your legs and your pelvis that experience a lot of normal loading or exercise through normal everyday life. We do a lot of standing, we do a lot of walking. All of that contributes to maintaining strong bones. Once you're not doing that anymore, when you're living in space, well, those bones start to degrade. You'll notice the bone with the least amount of change is the arm. Why do you think that is? Well, your arms aren't experiencing a lot of loading normally under Earth gravity, and they're probably experiencing about the same amount of loading in space, or maybe even a little bit more, because crew members, astronauts, tend to translate or move through the space station using their arms and hands more than their legs. Next slide. Cardiovascular adaptations to space flight. Well, when you take away gravity, your heart doesn't have to work as hard to keep blood circulating through your body. It's especially tough to move fluid up a long column. And if you think about your body when you're standing up, That's essentially a long column of fluid, and your heart has to be able to move fluid all the way from the tip of your toes all the way to the top of your head, and that's a lot of work. So your heart has to be strong to do that. Well, in microgravity, that blood doesn't weigh anything, so it's pretty easy to move it through your body. And as such, because your heart isn't working as hard, it gets weaker. The problem with that isn't so much while you're in space, but you do start to lose what we call cardiovascular conditioning, and that can become a problem when you get back to Earth. There's another interesting thing that happens. Your heart will actually shrink. You'll actually experience a decrease in your heart mass while you're in space. Next slide. This is an astronaut. It's an old picture. I apologize for that, but if you hit the next slide, you'll see what it looks like on Earth versus space. People look a little bit different in space because the fluids in their body tend to migrate toward their head. And there's a fun little experiment that you guys can do later. You'll hit the next slide. Use your camera phone or a digital picture. Take a picture of yourself or of a friend up against a wall. Try and get mostly their face in the picture. Next slide. Have them lie down with their legs up against that wall for about 10 minutes. And it's not very comfortable to do that. You'll start feeling, or your friend will start to feel the effects of your legs will get a little tingly and your face will start to feel a little bit puffy. And if you hit one more next slide, make sure you take a picture while they're still lying down, and you'll see a change just in 10 minutes of fluid shift. This is especially fun to do with younger brothers or sisters, because they don't know what's going to happen to them. And for the advanced students, if you have a tape measure, a fabric tape measure that you can wrap around their legs, your subject's legs, you can measure every minute or every 2 minutes the circumference of their leg at the same place, and you'll actually be able to measure their leg shrinking. So that fluid had to come from somewhere. It went from their legs all the way to their face. So that's a fun one you can do later. Next slide. You've learned a little bit about muscle changes in microgravity. There's a shift in fiber type. Your muscles go from slow to fast twitch. They lose ability for long endurance activity, and they become more able to do fast but weaker work. Again, that's not so much of a problem while you're living in space, because lifting and moving and working in a microgravity environment is really easy. The problem is when you get back to Earth. So muscle weakness is another concern, and in an upcoming slide, I'll show you how we try and prevent our muscles and bones and heart from getting weaker. Next slide. Cancer and radiation. This is certainly a big problem, and it's really hard to combat. It's just a natural fact of going to space. When you lose our atmosphere, the protection that our atmosphere provides us, you're going to be exposed to things like solar particles, galactic cosmic rays, and other high-energy particles that are trapped in our magnetic field. The result of those high-energy particles and cosmic rays is that if they hit DNA in a cell, these are very high-energy particles. They'll go right through you. And that's not the problem. The problem is if they hit DNA and they do some damage to DNA, and if that DNA keeps getting replicated, you can end up with some mutations, and eventually that could lead to cancer. So that's a concern of ours as well. Next slide. So how do we keep our astronauts healthy in space? Hopefully this is not going to be new information for you, because it's the same way that we keep you healthy.